Good morning, everyone. This is going to be the last lecture, and for the next two meetings, we will just have presentations. I have extended the last problem set to the end of Sunday, so we have enough time to do projects and also the homework. Thank you. Okay, so last time we talked about the hyperability results by assuming a stronger light tail assumption, the sub-Gaussian distribution. So let me recap the main theorem and the important corollary about the complexity. Okay, so this is the general hyperbolic bound we have for the stochastic subgradient method with sub-Gaussian detail assumption. And if we choose the subsize to be a constant as this minimum, then the complexity to find this hyperability guarantee is this much. The good, so the good property here is that we do not have 1 over p squared dependence on this small number p. Here p is between 0 and 1. It's a small number, close to 0. So the dependence on p, if you simply use Markov's inequality based on the convergence expectation, it will be 1 over p squared. But here you can see the dependence on p is always log of 1 over p, right? By making stronger assumption. So let's assume this theorem is true and then see how we can obtain this complexity. Because here gamma is arbitrary, it holds for any gamma greater than or equal to 0. So for our purpose, because here we want to show the primal gap less than or equal to epsilon is greater than or equal to 1 minus p. So it's sufficient to work with this bound by making this arrow here, this long arrow term here, to be on the order of epsilon, and to make this term to be on the order of 1 over, to be just p, right? So if probability of this is greater than or equal to epsilon is less than or equal to p, so it's equivalent, greater than or equal to epsilon is less than or equal to p, is equivalent to, say, this claim, right? So let's just make this part to be p. So to make this part to be p, we just need to take gamma to be log 1 over p. Right, if you take gamma to be log 1 over p, then exponential of minus gamma, this is just the p, right? And this is p squared on the order of p squared. P squared is much smaller than p, so this is a dominant term, right? So it's sufficient to take gamma to be log of 1 over p. If you want to be precise, we just need to play with the constant here, right? Somehow to adjust the constant here, but it's just on the order of p. This is just the log of 1 over p. Okay, so then let's make what's left to us is to make this long arrow term to be on the order of epsilon, and let's first simplify the notation here by taking all the lambdas to be this constant lambda, right? So what we have here is d0 squared over 2 lambda k, right? Here we have summation of 2 times summation lambda I, so this is 2 lambda k, right? So the first term is d0 squared over 2 lambda k. Here we also use the fact that lambda is no more than 1 over 4 lambda. So that we have another, so this will be bounded by 1/2, right? This denominator here is just bounded by 1/2, and it will cancel with the 2 from here. So what's left here is 4 lambda squared times m times k divided by lambda k. So the ratio is equal to 4 lambda m squared. And for this part, here we have a factor of square root of k, and here we have a 1 over k. So that's why we have 1 over square root of k here. And the last term, here for gamma, we also take gamma to be log of 1 over p, just loosely in the sense of the order, right? We ignore the constant. And here, the gamma also is taken as log of 1 over p. Here we have a factor of k. It cancels with this k. So this one goes to 0 at the rate of 1 over k. This is at the rate of 1 over square root of k. So they will be handled by, so the way to make these two terms to be small is by taking k large. And that gives us the complexity bound. Well, for these two terms, they do not depend on k. So the only way to make them small is by taking lambda small, right? And by putting them together, so we have lambda times 4m squared and so we want sum of the two to be upper bounded by just epsilon over 2. And this means our lambda has to be no more than the first term here. Right? By taking lambda small, you can make this part small. This is like the proof in the subgradient method. There's always an error on the order of lambda times m squared. So that's why in subgradient, you always take lambda to be small as epsilon over m squared. This is for the same reason. As I mentioned last time, in stochastic optimization, this variance term, sigma, plays the same role as the Lipschitz constant, m. So if you view this p, log of 1 over p as a constant, then these two play the same role, right? So lambda is on the order of 1 over m squared or 1 over m squared plus sigma squared. That's the same order. So this part explains why lambda has to be this small, and this actually comes from the convergence proof for one step, and it also plays a role here by making lambda this small. The numerator here is always positive. The denominator here is always positive. Okay, and for the last two terms, so for this part, for example, let's make d0 squared over 2 lambda k be less than or equal to epsilon over 4. Okay, so this gives you a bound on k. So k is on the order of d0 squared over lambda epsilon, right? And by plugging in value of lambda, so lambda is minimum of two terms. So then lambda is in the denominator, then this bound on k becomes a maximum of two terms. That gives you these two that gives you these two terms, right? This one comes from 1 over 4 lambda. This part comes from the first term here, right? And the last term, it comes from this bound. So we have another bound on k, right? This k gives you this bound. So in the end, you just take the maximum of these two terms and the maximum of this one. So it's maximum of 3 terms, right? So this explains how we obtain this good dependence on p as log of 1 over p. Because you just choose gamma to be log of 1 over p. Here we have the freedom of choosing gamma. Okay. Okay. Now let's see how to show the proof of the main theorem. Recall that when we show the convergence expectation, we have this one-step convergence result. Right? This is what you can claim from the one step of the proximal stochastic subgradient method. And then now let's make some new observations. So let's call this term as zeta. And let's call this distance of subgradients as delta. So then this one-step result becomes right here. We just call this as zeta k, and this term becomes lambda square delta k square. Okay, then we sum this inequality. Here, all the summations are from 0 to k minus 1. Okay, so these steps looks very familiar to us. We always do this even in the convergence expectation result. So let's make some observation about this term here. Recall that we have the sub-Gaussian distribution for the tail. Okay. So the first observation here is that given the sequence of all the randomness you have so far, then this zeta k, this conditional expectation is 0, right? Because zeta k conditioning on the randomness you have so far, then xk becomes deterministic, right? Because xk is a function of this randomness, right? This sequence of random variables. So given this sequence xk is deterministic, so if you take expectation of this zeta k, then it's equal to, so you only take expectation of this difference term, right? And because of the unbiasedness of this stochastic subgradient oracle, expectation of this s is equal to f prime, right? So the expectation of this zeta k conditioning on the randomness is just 0, right? So this is 0. And the second observation is about the variance of this term. So this really comes from the sub-Gaussian detail assumption, sub-Gaussian tail assumption. So here, the first inequality is by Cauchy-Schwarz and the boundedness. So here, zeta k is bounded by lambda times the norm of this difference and the norm of this difference, right? The norm of this difference is just the delta k. And here, the norm of this difference, xk minus x star, because they're all in the domain of h, and so it's bounded by the diameter d, right? That's why we have this bound here. And then these two constants cancel out. So what's left is just the delta k square over sigma square, and take the exponential and then expectation. This is exactly the same as what we have here, right? Here we ignore that sequence, but if you are considering about the sequence and give this c k minus 1 this sequence of random variables, then they are the same thing, right? So it's upper bounded by exponential 1, just the e. Okay, we also need to recall a technical lemma we had before, but we didn't prove. So for a sequence, last time we claimed that for a sequence zeta k, if the expectation of zeta k, conditional expectation, so the lemma we had last time was about the sequence of zeta k. The first condition on zeta k is exactly the same as what we observe here, right? Given this sequence of random variable, then the conditional expectation of zeta k is 0. And the second assumption was similar to this one. So the expectation of exponential zeta k square over, this is a deterministic number, sigma k square, conditionally on the sequence of random variable is upper bounded by exponential of 1. Then we can claim this concentration inequality. This was basically proved by using Chernoff bound. So, and also this part explains the source of this term, exponential to the minus gamma square over 3. And this holds for any gamma greater than equal to 0. Since now the zeta k in our analysis really, these two observations really satisfy the two assumptions we have here. So now we can apply the concentration bound on the zeta k. When we apply this bound, we note that here we have okay, so here the sigma k is actually this term here. This is our sigma k, right? What's varying is not this sigma, but this lambda k. So now we just need to plug in value of sigma I. Sigma I is lambda I d square, right? And because d and sigma, because d and sigma can be factored out of the square root. So what we have is quite similar to this bound. So basically, this part handles this term, right? Here we are interested in summation of zeta I, and here it gives a concentration bound on the summation of zeta I. So we will use this result later, but this is a partial result about this term. And now let's focus on this term here. This is summation lambda I, delta I, and here delta I is this difference of subgradient. And so basically we are going to use the subgradient, sub-Gaussian distribution as a tool to give a concentration inequality bound on that term. And so it starts from this observation. Because exponential is a convex function, so we have this bound using convexity. But here it's just view this as f of xi, and here we are just averaging this function, right? This is the parameter, combination parameter. So because it's convex, we can put all the parameter inside the function, right? So this is just by convexity of exponential. And now let's take expectation of this inequality. So the left-hand side is just expectation of this term. And for the right-hand side, because this is, you have this linear structure, so it's combination of expectation of this exponential, right? And each single term, exponential of this, each single term, you can use sub-Gaussian bound, right? So it's upper bounded by exponential of 1. And here you are just, this sum is just 1, right? This is a combination, so it's also upper bound. This expectation is also upper bounded by exponential of 1. Right? Then because this is just a bound on expectation, to turn a bound of expectation to a bound on probability, usually we just use Markov inequality. Right? Now let's use Markov inequality to obtain a property bound. So the probability the first, this identity is just, we just take exponential of both this left-hand side and right-hand side. So then the probability if this greater than to this is equal to probably the exponential of this term greater than to exponential of this term, right? So this is just identity. And from here to here, we are using Markov inequality, right, to turn probability bound to a ratio of exponential with a constant. And then here we are using this partial result. So you can check the algebra by putting Markov inequality and that observation together. We have this concentration inequality to bound this term here. Okay. And then, so this is the concentration for the last term, And this is the concentration inequality for the third term. Now we can put everything together to obtain the final result. Put that result here. So for the third term, I'm going to call this long term as just error. So this is our goal, right? To derive an upper bound on this probability. That's the goal here. And to upper bound this one, we need to make use of this inequality, right? Because we know this primal gap is always upper bounded by this right-hand side right here. So then the probability that this is greater than or equal to the error is no more than the probability that this right-hand side is greater than or equal to the error, right? Because this is always less than or equal to the right-hand side. So that explains this bound, the right-hand side here, because comparing the error with this term, you can cancel out the first and the second terms. Right? They're the same. So the first term here is the same as the first term in the error, and second term is also the same. They can be canceled out. Right? So what's left is just the third and the first term, and this ratio can also be, this denominator can also be canceled. They both have this 2 times summation lambda I, right? So after simplification, we just have this bound here. Third term plus last term greater than or equal to these 2 bounds, right? These 2 bounds are from here. And to upper bound this inequality, we use the sum of 2 probabilities. To upper bound this probability, we use the sum of these 2 probabilities. This comes from a simple observation that, so here we're using the fact suppose x and y, they are two random variables, and a and b are two scalars. The probability that the sum of x and y is greater than to a plus b is no more than the probability that if any of these two events happen, right? So for the sum of x and y to be greater than to a plus b, you must have either x greater than to a or b, y greater than to b. If none of them happen, then this cannot happen, right? So this is less than to this probability. And this is by the union bound, right? Probability of a union of two events is no more than the summation of this, the probability that each event happens, right? So this is by union bound. This is just by logic, okay? And apply this observation, this fact, to the inequality here. This is x, this is y, here's a and b, right? So we can separate this probability into two probabilities. And the first one here is this partial result, right? And the second bound is it's here. It's this bound, right? So this is 2, and this is 1. Right, and then putting them together, you have the sum of this exponential and the exponential of minus gamma, which explains this upper bound. Okay, so that completes the proof. Any questions? Yes.
So the term there for the inequality of the exponential being less than or equal to the convex combination. So are we just treating delta I as the free variable there when we treat it as a convex combination? Just because if we treat the true gradient as fixed, so
you don't need to think about the randomness here. Just view this as some number.
okay.
Or some scalar delta I.
Okay.
Okay, so delta I is these are like x1, x2,
Right.
to xn. Okay, so that completes the lecture on stochastic optimization. So we began from a motivating example of sampling, and then we draw the connection between sampling and so by switching in sampling, we try to minimize the KL divergence of some rho and the target distribution pi. By switching them and parameterize the distribution, you can rewrite this problem as an MLE, right? Maximum molecular estimation. And then we reformulate the maximum molecular estimation as an optimization problem, which is a stochastic sample average approximation of the stochastic optimization problem. Then we talked about two approaches, two standard approaches in stochastic optimization. First is SA, stochastic approximation, and then SAA, that is sample average approximation. Here you need to take a large number of samples to approximate the function, the stochastic function, and then use any deterministic optimization algorithm to solve the approximation, right? Then the problem is how many samples I need to take, how to quantify the intuition of law of large numbers. And that is what we covered in the lecture on SAA. to give you a probability bound on the number. So you basically have a convergence rate, how you SAA is good as an approximation to the SO, the stochastic optimization. And in the recent two lectures, we talked about sample approximation, which is an online algorithm. You do the optimization together with the sampling procedure together, step by step. You do not take sample first and then do an offline optimization, but they are combined together. And we first gave an analysis on the convergence expectation. And then in this lecture, we give the proof on high probability results. But to obtain this high probability results with a good dependence on the p, the small number p, right? P is close to 0. To reduce the dependence from 1 over, to improve the dependence from 1 over p squared to log 1 over p, you have to make this the sub-Gaussian tail assumption, which is a light tail assumption, right? And then with these concentration bounds, then we can get this good result, right? So this lecture is a little bit different from what we have seen previously, because here we use a lot of probability tools. That's because we are handling with stochasticity here. But previously we are just working with deterministic algorithms. But the only exception is for the lecture on the randomized coordinate block descent method. But the nature here is different because the problem is deterministic. It's just that the scale is too large. So we are using a randomized algorithm. So it's the algorithm is randomized, but the problem is deterministic. Here it's different. The problem itself is stochastic. Okay. So that basically concludes everything I want to talk about first order methods. I'm sorry I cannot cover what I plan to do. I had a very ambitious goal at the beginning to cover many topics, especially those applications in machine learning. I wanted to cover manifold optimization, distributed optimization, and also reinforcement learning. But I think I don't have time to do manifold optimization. Well, for distributed optimization, I partially covered it in the lecture on ADMM, right? I give you some example there, how to do the decomposition. Well, so what's left in my original plan was reinforcement learning and also second order methods and the high order method. So I don't have the notes for these two second order and also higher order methods, but I have the notes for reinforcement learning. I have already posted on the Blackboard, so you can read this by yourself. Let me see if I have time to briefly cover this in today's lecture. Right now, let me try to quickly give you an introduction to these two methods. So the first second order method that you might learn in any lecture, for example, in numerical analysis or in any optimization course, maybe Newton's method, right? With Newton's method, we do the update in this way. suppose we want to minimize f of x in Rn, we have no constraint, no composite function. And this is the Newton's method that you usually do, right? But this update can also be reformulated as an argmean. So this is what we are minimizing here is the linearization plus a quadratic term. Basically, this is like a second-order Taylor's expansion of the function f around the point xk, right? So by taking the gradient of this one to be 0, you have 0 equals right. So rearranging the terms, then you can show xk plus 1 as a solution of this optimality condition is equal to this update, which is Newton. Right? So this is the subproblem that is behind the scene for this update, right? And comparing this one to the gradient method, comparing with gradient descent. Both methods are using a quadratic function as an approximation to the function f. But here we are using, basically this is equal to 1 over 2 basically we are using lambda times identity, a diagonal matrix, to approximate this Hessian at the point xk, right? So this is an approximation to the Hessian. So Newton, the reason why Newton is better because it has a better description of the local geometry. We are using the exact geometry, the Hessian here. But here, we are approximating the Hessian by a diagonal matrix. And this lambda, recall that this lambda we usually take to be 1 over L. L is the smoothness of the function, right? And when Hessian exists, then we usually say this is upper bounded by L times I. And L can usually be viewed as the maximum eigenvalue for the Hessian. So basically, you are using this diagonal matrix with upper curvature to approximate this Hessian matrix here. Right? That's the approximation we have. Yes.
So would it be lambda to the -1 times I?
Yes. Yeah.
Okay.
Yeah. And lambda inverse becomes L. Yeah. So this is approximation we do in gradient descent. So there are, with this observation, there can be some extensions to Newton's method. For example, okay, so another way to compare these two is that the Newton's method has the benefit of a better local geometry, but here we lose some information. But the gain here is that with this simple lambda, this simple estimation, if lambda is 1 over L, then you can make the computation here much simpler than this one, right? Because you do not need to estimate this Hessian, do not need to do the Hessian inverse. So you avoid the outer n cube calculation, right? But here it's very simple, but you lose some geometry. That's why Newton's method has a good local convergence. It's quadratic convergence, right? But for this one, we do not have good local convergence. So here, because this is a second order approximation, what if the function has higher order derivatives? For example, if the function f has third order derivatives, you may also use the third order derivative, third order Taylor's expansion as an approximation, a local approximation, right? And then minimize that method. So in that line of extension, the method is called Taylor gradient, no, Taylor descent. Right? It's a way to generalize Newton's method, and you can always approximate the highest order derivative using some geometric information. But I will not go into the details. This is just one line of extension. And another way to extend it is from the perspective of how this method comes out. So here, one way to view this method is as this is a second order approximation, but we even further approximate the Hessian matrix by this diagonal matrix. That's one understanding. Another understanding is I just do first order approximation, but first order approximation is not stable. I want to stabilize or regularize this objective function. So I add a regularization here. Because this is first order approximation, so I add a higher order regularization, which is second order, right? So we can do the same thing to Newton. Newton is doing a second order approximation compared with this is first order approximation. So you need, if you want to regularize this step, you need to add a one order higher approximation or regularization, which is a third order regularization, right? So sometimes people just use 1/6 times m. People usually just add a third order term as a regularization. And if you minimize this objective here, the quadratic approximation plus the third order regularization, this is called cubic Newton.
Sorry, could you repeat why you want to regularize in this case?
Just follow this idea here.
Oh, okay.
Right here we add something to, because if you just minimize linearization, you have, and this is unconstrained, so this can go to negative infinity.
Yeah.
Right.
Okay.
So this is not stable.
Okay.
But adding a quadratic make it stable, right? And this is the same idea by adding a regularization term to improve the performance of the algorithm. And there are some theoretical guarantee for cubic regularization Newton. Okay, so suppose the Hessian is now is L Lipschitz continuous. Previously we used this L to denote the Lipschitz constant for the gradient f, right? Now we use this. We use the same L to denote the Lipschitz constant for the Hessian. So let's now ignore this L here. But it's just it's just describing some local geometry. Okay. But this is not local. This is for any x and y. So recall for Lipschitz continuity. This is a definition for Lipschitz continuity. Now we just extend it from gradient to Hessian. Okay. So with this assumption, we can show Okay, so for cubic Newton, we do not assume, here we just make this smoothness assumption, but we do not make any convexity assumption. So we do not need to make, we don't need to assume the function f is convex. Okay, and then we are looking for a local minimum. So previously, when we talked about non-convex optimization, you just look for a point fx star, gradient of fx star is 0, close to 0, right? We look for a stationary point. But now, since you have the hash information, you can look for something stronger, that is a local minimum. Right. If you also require the Hessian at this point to be positive semi-definite, then this is a local minimum, right? Because this is at this point locally, it's convex, right? This means it's convex and also you achieve stationarity. So this is a local minimum. But globally, this may not be the case, right? You may have other better minimum, right? So this is just a local minimum. But this is stronger than the different point we had before. Previously, if you just have this condition, different point, it can be this local maximum or even a saddle point. Okay.
What if you have a saddle point that's even higher than the Hessian? The order of the saddle point is higher than Hessian.
This point is a saddle point, but no, not this one. I mean, something like x cubed. At this point, they're both. Oh, but so we do not have this such a point. This is a saddle point because here it's just stationary. You only have stationarity, but you do not have this positive semi-definite Hessian, right? Okay, so in the algorithm, we cannot expect any point to be exactly 0, the gradient to be exact 0, and Hessian to be exactly negative, positive semi-definite. So this is just approximate 0, and this can be negative, but this can be non-positive semi-definite, but not far away from a 0 matrix. Okay, so what we can guarantee, so let's define this quantity. Oh, and again, this M can be the same as L if you know L, right? If you know L, you can take M to be L. But if you don't, you just use an estimate, like what we do for gradient type method. This can be obtained from an adaptive approach. You can do a line search, right? A backtracking. Test some condition. If it fails, you halve this quantity, right? And then try it again until some condition satisfies, which the condition should be the essential inequality for convergence. Okay, so the idea is very similar because basically this is just an extension of this idea, right? So we just generalize this smoothness assumption and also generalize stationarity to local minimum, and then the analysis is just more complicated, but the intuition is exactly the same. So for monitor the convergence, we need to define this new quantity and show this one goes to 0. Basically, this quantity is a maximum of 2 terms. Here we monitor the stationarity. Here we monitor the Hessian, the minimum of this minimum eigenvalue of the Hessian. Okay, this is always non-negative. This quantity here, because it's maximum of the 2. Right, this is always non-negative. if the Hessian matrix is at a certain point x is always positive semi-definite, then this becomes no more than 0, right? So this one will. So then you do not need to worry about the Hessian, but you only worry about the stationarity, right? So we just take the maximum for the two. And the main result we have here. Okay, so for simplicity, suppose we know L, and then we take the M to be L in the algorithm, and every iterate is obtained by minimizing this objective. Here we also take M to be L, right? Then this mu quantity on the iterate xi, and then take the minimum over all the iterates. This is upper bounded by this term here. So you have the convergence rate of 1 over square. You have 1 over k to the 1/3. This is a global convergence guarantee, different from Newton, which is gives you a local convergence. But this is global. And also here, do not need to assume the function f is convex. And you can even have some guarantee on the function value if you assume convexity. But I will not cover that, but just give you some main results. So if you assume convexity, then for cubic Newton, the convergence rate will be 1 over k squared. This is in terms of function value. And cubic Newton can also be accelerated, just like gradient method. You can do acceleration, but it will be more complicated. Then for accelerated version, you can improve this rate to be 1 over k cubed. But this is not the optimal, because the lower bound is actually one over k to the 3.5. So this is better than the lower bound is better than this algorithm's upper bound. So there is a gap, right? And the optimal one so there is an optimal second law method that gives you this matching upper bound. And this is obtained by using the accelerated inexact proximal point framework. So that's, yeah. This is a place where you can really see inside prox point is quite powerful. So people use accelerated version of IPP framework for second method, and that gives you this matching upper bound. And it's nice that this is not only optimal for second method, but also for higher order methods. So here, when we say the lower bound is this much, we need to confine our class of algorithms. So the class of algorithms only require you to know all the information of the function up to second order information. You can have access to zero order function value, right? First order the gradient information, and also second order the hashing. So within that class of algorithms, the best is this rate, and this optimal method based on accelerated IPP framework gives you this bound. And in higher order method, when we have more access to the function oracles, for example, you can have third order derivative, fourth order derivative, right? In that case, suppose you have the information up to the piece order. So for piece order, p greater than or to 2. The lower bound is omega 1 over k to the 3p plus 1 over 2. And the optimal method, also based on the accelerated IPP framework, gives you the matching upper bound. So it is optimal as always, but the accelerated higher order Newton method is not optimal. This is k to the p plus 1. For example, let's take p to be 3, then this one gives you k to the 5, right? But this gives you k to the 4. So this is better than accelerated Newton. And also when p is 2, that is our case, right? You have k to the 3.5, this is just k to the 3. And this even holds for p less than or equal to 2. For example, when p is 1, when you just have smoothness, the gradient is Lipschitz continuous. Accelerated method gives you, in that case, they coincide. They're the same. In that case, both methods becomes to the next of accelerated gradient method. They're the same, but in higher order method, you can see the difference. Okay, I think that's everything I want to cover. So next time we will have the presentation. So please remember we need to come around before 9:30. So we will start 10 minutes earlier so that we have enough time to set up. Okay.
Have a good day.
这是个 master。